If the sun went dark tonight, what would really happen? What if the sun went dark tonight, not in 5 billion years, not after a dramatic explosion? Just gone. One moment daylight, the next, a sky that snaps to black. Would Earth instantly freeze into a dead, airless ice ball? Would every trace of life vanish in a heartbeat? Or is there something, somewhere on this planet, that could keep breathing in the dark? This is more than a disaster movie thought experiment. It is a very real scientific question about how deeply life depends on a star. We build our entire idea of a habitable planet around starlight, around how far it orbits inside a Goldilocks zone. But while that framework works beautifully for Earth, like worlds bathed in gentle sunshine, it may blind us to something far stranger. So, let's begin with our own world. If the sun vanished tonight, the first thing we would notice is not the cold. It would be the silence in the sky. Within minutes, the blue would fade to a deep, empty black. The moon would disappear. The planets would vanish. Only the distant stars of the Milky Way would remain, suddenly sharp and indifferent. Within hours, Earth's surface would start to cool. The atmosphere, no longer heated from above, would bleed its warmth into space. Temperatures would plunge well below freezing in days. Oceans would begin to crust over with ice. Photosynthesis would stop almost immediately, cutting off the base of nearly every food chain we know. This means crops fail, forests suffocate, and the oxygen factory of the planet grinds to a halt. Human civilization, so delicately tuned to sunlight, would be in immediate crisis. Power grids would strain and then fail. Cities would be lit only by the brief glow of their own burning fuel. Even if we had stockpiles and technology, we would be fighting a losing battle against a world that is rapidly turning into a cryogenic tomb. So it's time to find out the truth. Does the loss of a star mean the automatic death of life? It should be noted that the answer, even on Earth, is already more complicated than it seems. Deep under the ocean, at hydrothermal vents, entire ecosystems thrive on chemical energy, not sunlight. In the rocks beneath our feet, kilometers down, microbes sip energy from radioactive decay and water rock reactions. If the sun went dark, these hidden biospheres might barely notice. And that raises a much bigger question. In the hunt for alien life, we usually focus on bright, welcoming stars and neat Earth like planets in comfortable orbits. But astronomers now suspect there could be more starless, rogue planets drifting through the galaxy than there are stars themselves. Optimistically speaking, some of those frozen, lightless worlds might still be warm inside. Could such a planet be alive without ever seeing a sunrise? And if it is, how would we detect a biosphere wrapped in eternal night on a world that does not even have a star to guide us to it? Why this question changes how we search the universe. If that sounds like pure science fiction, it should be noted that the way we currently do astronomy almost guarantees we would overlook such a planet. For more than a century, we have quietly built an assumption into everything that a world means a planet in orbit around a star. In the hunt for alien life, we talk about the Goldilocks zone, the habitable ring around a sun where liquid water can exist on the surface. We design exoplanet surveys to watch stars dim as planets cross in front of them. We analyze how starlight filters through an atmosphere to search for oxygen, methane, or water vapor. Almost every piece of data, every clever detection trick, begins with a bright central beacon. No star, no signal, or so we have told ourselves. But while this picture works beautifully for Earth, like planets around normal stars, real planetary systems are chaotic. Planets migrate. They scatter off each other. Gravitational encounters with passing stars can tear systems apart. The natural byproduct of this gravitational pinball is a huge population of rogue planets flung into interstellar space. Some microlensing surveys already hint that these dark worlds could be as common as stars. Optimistically speaking, there might even be more of them. This means that if life can adapt to a starless existence, we may be ignoring the majority of potentially habitable real estate in the universe. A thick hydrogen atmosphere on a drifting Earth-mass planet could trap internal heat for billions of years. Geothermal energy, radiogenic decay, or tidal heating in a captured moon system could power oceans beneath global ice. No sunrise, no seasons, but stable energy all the same. And if biology only needs liquid water, chemistry, and time, who says it cares whether a star is shining overhead? The stakes are enormous. If living ecosystems can arise, or even thrive, on these hidden planets, then our current search strategies are deeply biased. We are staring at the brightest objects and asking where life might be, while whole biospheres could be quietly evolving in the dark between them. A universe where life does not need a star is a universe where life is more resilient than we imagined, able to outlive its home star and migrate into interstellar night. It could be older than our sun, more widespread than our telescopes suggest, and far harder to extinguish. So, let's begin to widen our view. In the next part, we will dive into Earth's own dark ecosystems, from deep sea vents to the deep biosphere, and ask whether they are prototypes for life on starless planets. Then, we will push outward again to theoretical rogue worlds and the tools that might finally let us detect a living atmosphere without any guiding star. So it's time to find out the truth. What does habitable zone really mean when the lights go out? Meet the star of the story, our sun and its hidden dependencies. If we want to imagine life without a star, we first have to face an uncomfortable fact. We live in the glow of one, and nearly everything we know about habitability is filtered through that light. So, let's begin with the star that defines our lives. The sun is a middle-aged G-type star, about 4.6 billion years old, roughly 1.4 million kilometers across, and more than 300,000 times the mass of Earth. Its surface simmers at about 5,800 degrees Celsius, with a core hot enough for nuclear fusion to turn hydrogen into helium and flood space with energy. In the grand catalog of the Milky Way, it should be noted that the sun is not rare or extreme. It is almost boring, but for us, it is everything. How much of Earth's story does that boring star actually write? If we total up our planet's energy budget, around 99.9% of the energy driving our climate and surface temperature comes from solar radiation. Sunlight warms the ground, powers winds and ocean currents, and sets the average temperature that keeps water liquid over much of the surface. Deep inside Earth, radioactive decay and leftover formation heat contribute the remaining fraction, only about 0.1% at the surface, leaking out through volcanoes, hot springs, and the slow creep of plate tectonics. This means that, from the viewpoint of a tree, a bird, or a human, the sun is the central power grid. Photosynthesis captures a tiny slice of incoming sunlight and turns it into chemical energy, locking it into sugars and biomass. Almost every surface ecosystem, from tropical rainforests to open oceans, rests on that trick. Plants, algae, and photosynthetic microbes feed herbivores, which feed predators, which feed the scavengers and decomposers that close the loop. At the same time, photosynthesis constantly refreshes atmospheric oxygen. Without that solar-driven process, complex, active life like us would quickly suffocate. But while nearly all the visible biosphere is indirectly solar-powered, not every ingredient of habitability answers to the sun. Gravity, for example, depends on mass, not starlight. A planet's ability to hold an atmosphere, run plate tectonics, or keep a molten core is set by its size and composition. Internal heat from radioactive decay will keep flowing for billions of years, star or no star. Chemistry, too, does not care if reactions happen in daylight or in total darkness, as long as there is a source of energy and a way to move electrons. Here's the pattern interrupt. What if we turn the lights off, right now? Deep beneath our feet, many ecosystems barely notice. Microbes kilometers down in rock and entire communities around deep-sea hydrothermal vents live on chemical gradients and geothermal heat, not on sunlight. In the hunt for alien life, these are not just curiosities. Optimistically speaking, they might be prototypes for biospheres on starless, drifting worlds. So it's time to find out the truth. How far can those hidden, sun-independent strategies really go? Life in the dark? Earth's sunless ecosystems. If we want to know whether life could endure without a star, we do not have to imagine it from scratch. We just have to go somewhere our own sun has already been banished, the deep ocean floor. Picture this. 2, 3, 4 kilometers down, sunlight is gone. The water is near freezing, the pressure is crushing, and yet, in the blackness, we find glowing towers of rock called hydrothermal vents. Superheated, mineral-rich water blasts out of these chimneys at hundreds of degrees Celsius, mixing with the icy deep and creating shimmering clouds. Around them, forests of white and red tube worms, carpets of clams, swarms of blind crabs, all clustered in a tight ring of heat and chemistry. How do they live here, with no light from the star in our sky? The answer is chemosynthesis. Instead of plants capturing photons, microbes capture molecules. They take hydrogen sulfide, methane, and other reduced chemicals spewing from the vents and use their energy to build organic matter. This means the base of the food web is not green leaves, but thin films of bacteria and archaea-coating rocks living inside tube worms and lining the chimneys themselves. It should be noted that these are not small, fragile systems. Some hydrothermal vent fields support dense communities stretching for kilometers, with complex interactions, predators, and long food chains, all running on chemical gradients and geothermal heat. In the hunt for alien life, this is our first hard proof that a biosphere does not need direct starlight to be rich and active, and vents are only the beginning. Elsewhere on the seafloor, at so-called cold seeps, oil and methane ooze quietly out of sediments. There is no dramatic heat, just slow leaks of chemical fuel. Yet we still see mussel beds, tube worms, and strange, pale fish, all ultimately powered by chemosynthetic microbes. Entire deep-sea habitats operate like this, from whalefall communities to brine pools, showing that complex, multicellular life can be fully supported by chemistry alone. Then we go deeper still, beneath the seafloor and down into the crust. Here lies the deep biosphere, microscopic life hiding in rock pores and fractures, kilometers below Earth's surface. These microbes may weigh as much as, or even more than, all animals and plants at the surface. They survive on radiogenic heat from decaying elements and on incredibly slow reactions between water and rock, sometimes dividing only once in centuries. So, let's begin connecting the dots. Hydrothermal vents, cold seeps, and the deep biosphere are natural laboratories for starless life. They prove that as long as there is liquid water, a chemical disequilibrium to exploit, and enough time, life can persist in complete darkness. So it's time to find out the truth. If Earth can do this in a thin crust around a bright star, what could an entire rogue planet do, drifting alone between the stars? How little energy does life actually need? If a world drifts in darkness, how much energy does life really need to keep going? Because at its core, life is not about sunshine or even warmth. It is about chemistry refusing to settle down. Every cell is a tiny rebellion against equilibrium. Molecules are constantly being pushed uphill in energy and then allowed to roll back down in controlled ways. This means you always need some kind of energy source, some difference in chemical potential, to keep that cycle running. But does that source have to be strong, like a nearby star, or can it be almost unimaginably weak? On Earth, most of what we see depends on the sun. Photosynthesis at the surface is flooded with power. On a clear day, each square meter of ground receives around 1,000 watts from our star. Our entire climate, our oceans, our familiar idea of a habitable planet are shaped by that constant torrent. In the hunt for alien life, it is easy to assume that anything less is hopeless. But deep below our feet, the numbers tell a very different story. In the continental crust, there are microbes that divide only once every few decades, or even once in several centuries. Some estimates suggest individual cells may persist for thousands of years without ever fully waking up in the way we imagine. And yet, by every reasonable definition, they are alive. They repair DNA, maintain membranes, and over long timescales, they evolve. The energy flux they survive on is astonishingly small. Instead of hundreds of watts per square meter, they may live on billionths of a watt per cubic centimeter, powered by radiogenic decay in the rock, slow corrosion of minerals, or the faint trickle of hydrogen and methane from geochemical reactions. It should be noted that if we scaled human society down to that energy budget, our entire civilization would flicker out almost instantly. So, let's begin to think in terms of a minimum viable biosphere. Imagine a rogue Earth-like planet with no star at all, its surface frozen solid, but its interior still warm from radioactive elements and lingering formation heat. A thick crust insulates that interior. Tiny pockets of liquid water form around fractures and hydrothermal systems. In those pockets, sparse microbial communities tap into chemical gradients as slowly as our deep subsurface microbes do. The whole world is alive, but only in scattered, whisper-quiet oases, optimistically speaking. This means such dark biospheres could be stable for billions of years, outliving many stars. But here's the tension. If life can run on such a low-energy trickle, should starless, hidden ecosystems be common across the universe, or are we overlooking crucial bottlenecks that almost always shut them down? So it's time to find out the truth when we push energy to the absolute minimum. Does life fade away, or does something even stranger emerge on these lightless worlds? Who's talking to you, and where we're going next to answer that? We need a clear map. I am Alex. This is Deep Sky Questions, and whether you have been with us for the TRAPPIST-1 saga, or you are joining for the first time, we are going to stay right inside this mystery, and keep moving. No sponsor detour, no long channel speech, we have a universe of dark worlds to explore. So what are we really asking here? Not just whether anything could survive without a star, but which specific kinds of planets could do it? What kinds of worlds, powered by what kinds of energy, could host life in total darkness, and how would we ever know from light years away? In the hunt for alien life, that sharper question matters, because it turns a vague idea into something we can actually test. So, let's begin by building a toolkit. Before we chase any one exotic planet, we will lay out the basic energy sources that do not care whether a star is shining or not. Geothermal heat from a molten interior. tidal heating from gravitational flexing, radiogenic decay from radioactive elements, chemical gradients, like the ones that drive Earth's hydrothermal vents at the bottom of the ocean, where entire ecosystems thrive without a single photon of sunlight. This means we can talk about habitable in terms of physics and chemistry, not only in terms of distance from a Goldilocks zone. Once we have that toolkit, we will start applying it to actual worlds. First, rogue planets, worlds thrown out of their original system, drifting alone between the stars, perhaps wrapped in thick hydrogen atmospheres that trap internal heat for billions of years. Then, buried ocean planets, icy shells with liquid water oceans locked away beneath, like Super Enceladus or Super Europa, scaled up to Earth-like sizes. Finally, dimly lit planets on the outer edges of their star's orbit, where starlight is weak and internal energy has to carry most of the load. For each case, we will ask whether life could really persist there, not just for a moment, but for deep time. After that, we turn our eyes outward. How could telescopes, current and future, detect or rule out life on such dark or low-light worlds? We will look at how we might catch a rogue planet through microlensing, how we could read the atmosphere of a hydrogen-shrouded world, and what kinds of chemical fingerprints might betray a hidden biosphere. Even if the planet reflects almost no starlight at all, it should be noted that this is where the frontier of real data begins to tug on the edge of theory. The pacing will be quick, but systematic. To keep us grounded, we will keep returning to three simple words: energy, liquid water, and time. Here is the pattern interrupt. From now on, you are not just watching, you are keeping score. For every world we visit, ask yourself three questions. Does it have a stable energy source? Can it sustain liquid water somewhere, even if buried? And can those conditions last long enough for life to emerge and evolve? If a planet checks all three boxes, optimistically speaking, it stays on our list of candidates. If it fails, it drops off. By the end, we should have a small, surprising family of starless or nearly starless worlds that might truly be habitable, and we will see whether the idea of life without a star is a rare exception or a hidden rule of the cosmos. Beyond starlight, the alternative power sources for life to decide which of those worlds stay on our list. We first need to ask a deeper question. What actually counts as power for life when a star is gone? Because if sunlight disappears, something else has to pay the energy bills. So, let's begin with the most familiar alternative: geothermal heat. On Earth, our planet is still warm inside because it formed hot and never fully cooled, and because heavy elements deep down keep releasing energy. That internal heat drives volcanism, pushes the plates of the crust around, and powers the hydrothermal vents on the seafloor. At those vents, entire ecosystems thrive without a single photon from the sun, using hot, mineral-rich water as their energy gateway. In the hunt for alien life, those vents are not just curiosities, they are proof of concept. They show that a planet's interior can feed a biosphere, even if its surface is locked in darkness and ice. It should be noted that similar geothermal systems could exist on a rogue Earth-like planet drifting between stars, wrapped in a thick atmosphere, or buried under a global ocean. But internal heat does not only come from formation leftovers. There is also tidal heating, where gravity itself needs a world like dough. When a small planet or moon orbits close to a massive body on an elongated path, changing tidal forces flex its interior, turning orbital energy into heat. Io, the innermost large moon of Jupiter, is the most volcanic place in the solar system for exactly this reason. Its neighbor Europa and Saturn's moon Enceladus use the same effect to maintain deep subsurface oceans beneath ice. This means that even in a dim system around a red dwarf, or in a distant orbit far beyond the traditional Goldilocks zone, a moon can stay warm inside just by being pulled and squeezed. Optimistically speaking, a rogue planet with a captured moon, or a compact multi-planet system, could host similar tidal furnaces in the dark. Underneath both geothermal and tidal heating lies another, slower engine: radiogenic decay. Long-lived radioactive isotopes such as uranium, thorium, and potassium are scattered through a rocky planet's mantle and crust. As they decay, they drip-feed heat into the interior over billions of years. On Earth, this radiogenic power is a major part of our internal energy budget, quietly keeping the core and mantle active long after the surface cooled into solid rock. Heat alone, however, is not enough. Life needs usable differences, not just warmth. That is where chemical gradients come in. Whenever oxidized and reduced materials meet, or two fluids with different compositions mix, there is a chemical imbalance. Microbes at Earth's hydrothermal vents exploit these redox contrasts, pulling energy from hydrogen, methane, sulfur, and metals instead of sunlight. Similar gradients exist in deep rocks, in cold seeps, even inside ice. So it's time to find out the truth about starless worlds. We should picture each planet as a kind of battery. Geothermal, tidal, and radiogenic processes charge it from within, while water, rock, and any remaining atmosphere act as circuits. Life, if it appears, only has to plug into one of those circuits, and some of them do not care at all whether a star is shining overhead. In the next section, we will test how long those hidden batteries can stay charged, and whether any of them can power a truly habitable world for billions of years in the dark. Rogue planets, the galaxy's homeless worlds. So, if some of those hidden batteries can run without a star, where do we actually look for them? There is one category of world that almost seems built for this question: rogue planets. The galaxy's homeless worlds. A rogue planet is a planet that does not orbit any star at all. It drifts through interstellar space, unbound, with no sunrise and no sunset. Some of these worlds were probably born in normal planetary systems, like our own, and then, through violent gravitational encounters with giant planets or passing stars, were thrown out entirely. Others may form more like tiny failed stars, when small gas clouds collapse but never gain enough mass to ignite. In the hunt for alien life, these are the ultimate outsiders. It should be noted that we have never taken a clear picture of an Earth-like rogue world. Instead, we infer their existence from very indirect data. One of the most powerful tools is called gravitational microlensing. When a compact, dark object passes in front of a distant star, its gravity briefly magnifies the star's light. For a few hours or days, the star appears to brighten and then fade again. By measuring the timing and shape of that brightening, astronomers can estimate the mass of the invisible lensing object. Some of those lenses are too small to be stars, yet too massive to be dust. They look exactly like planets, wandering alone. Here is the startling part. When we add up these microlensing events, some studies suggest there could be at least as many rogue planets as stars in the Milky Way, and perhaps far more. This means that the most common type of planet in our galaxy may be one we almost never see, drifting between the stars in perfect darkness. Optimistically speaking, that is an enormous amount of real estate for potential biospheres. But what would conditions actually be like on one of these worlds? Imagine an Earth-mass planet that is suddenly ejected from its system, no more sunlight. Within weeks, the surface temperature would plummet, the oceans would begin to freeze from the top down, locking the surface in a thick shell of ice. Any remaining atmosphere would collapse, snowing out as liquid nitrogen or carbon dioxide, leaving a thin, almost airless skin. On the surface, you would see only endless night, cryogenic cold, and a dead, frozen landscape. It does not sound habitable. But while the surface becomes a cosmic deep freeze, the planet's interior does not simply switch off. Radioactive elements are still decaying. Rock is still slowly moving. Internal heat, as we have seen on Earth, does not care about starlight. So it's time to find out the truth. Under that global ice shell, could liquid water survive, perhaps for billions of years, and could chemistry there stay active long enough for life to arise? In the next section, we will push into that darkness and ask whether a starless ocean world could secretly be more habitable than some planets inside the classic Goldilocks zone. Steppenwolf worlds, oceans beneath eternal night. So, let's begin with one of the strangest ideas in modern planetary science. Imagine an Earth-like planet, but there is no star in its sky. No sunrise, no seasons, just eternal night. It drifts alone through the galaxy, a world without an orbit around any visible sun. Astronomers have a name for this kind of world, a Steppenwolf planet, wandering like a lone wolf through interstellar space. On the outside, such a planet would look utterly dead. Surface temperatures would plunge to hundreds of degrees below zero. Any surface oceans would freeze solid, building an ice shell tens or even hundreds of kilometers thick. But while the surface becomes a cosmic deep freeze, the interior does not forget that it once formed hot. Radioactive elements still decay. The core still cools. Heat still flows upward. This is where insulation physics quietly becomes the star of the story. Ice is not just cold, it is an excellent thermal blanket. A thick ice shell, perhaps topped by a thin atmosphere of nitrogen, carbon dioxide, or even hydrogen, slows the escape of geothermal heat. At some depth, the pressure increases, the temperature rises, and the base of the ice can reach the melting point of water. This means a stable ocean can exist sandwiched between rock below and ice above, even when the universe outside is almost at absolute zero. If that sounds speculative, it should be noted that we already have proof of concept examples in our own solar system. Europa orbits Jupiter, Jupiter, Enceladus orbit Saturn, and both live far beyond the classic Goldilocks zone. Their surfaces are ice, but data from spacecraft tell us there are global oceans beneath, kept liquid by tidal flexing and the same slow radiogenic heat that warms Earth's interior. In the hunt for alien life, these icy moons have become prime candidates precisely because they show that liquid water does not require direct sunlight. On a Steppenwolf planet, the heating would be mostly internal rather than tidal, but the potential energy sources for life look surprisingly familiar. At the rocky seafloor, hydrothermal vents could spew hot, mineral-rich fluids into the dark ocean. Water rock reactions, such as serpentinization, can generate hydrogen gas and other chemical fuels. Microbes could tap these gradients the way deep-sea ecosystems on Earth do, building food webs without a single photon. But how rich would those webs really be? Without a star constantly pumping energy into the system, the total power budget is far lower than on a sunlit planet. Optimistically speaking, there might be thick microbial mats clustered around vents, slowly cycling carbon, sulfur, and iron. More pessimistically, the ocean could be a vast cold volume with only thinly scattered cells, each dividing perhaps once in centuries, a biosphere stretched out over deep time. So it's time to find out the truth. Are Steppenwolf oceans potential cradles for complex ecosystems, or are they more like biological crypts, barely alive? In the next section, we will compare these starless seas directly to Earth's own deep biosphere, and ask how we could ever detect such hidden life from light years away. Hydrogen blankets, turning dark worlds into hidden oases. So if Steppenwolf worlds are the bare-bones version of starless habitability, what happens when nature adds something extra? What if a rogue planet does not just cling to a thin crust of ice, but wraps itself in a colossal, invisible blanket? In the hunt for alien life, this is where things get very strange. Imagine an Earth-mass planet, flung out of its original system, drifting between the stars. But instead of losing its air to space, it keeps a massive, primordial hydrogen atmosphere, tens to hundreds of bars thick, pressing down like an ocean of gas. At first glance, that sounds useless. Hydrogen is transparent, almost boring. How could that possibly keep anything warm? This is the twist. Hydrogen lets visible starlight pass through easily, yes, but at high pressures it starts to behave differently. Molecules collide so often that they briefly form pairs and clusters, and those collisions allow the gas to absorb infrared light that a thin atmosphere would simply let escape. This process, called collision-induced absorption, turns a clear gas into a powerful, broadband greenhouse. The planet's own internal heat tries to radiate away into the cold of interstellar space. The hydrogen blanket catches it and sends it back down. It should be noted that we are not talking about a gentle, Earth-like climate tweak. Modeling work suggests that with a thick enough hydrogen envelope, a rogue planet could keep surface temperatures above the freezing point of water for billions of years, with no star at all, no Goldilocks zone, no red dwarf required, just residual heat from formation, slow radioactive decay in the interior, and an absurdly efficient insulating coat. But what would it feel like to stand there? The surface might lie under a crushing pressure, perhaps dozens of times Earth's. The sky could be a deep, hazy blue or gray, maybe laced with high clouds of water or methane. There would be no sunrise, no sunset, only a permanent dim glow. Starlight scattered from distant dust, the soft band of the galaxy overhead. Perhaps bright enough to navigate by, but never bright enough to cast sharp shadows. Shallow seas or even global oceans could roll under that sky, stirred by slow winds and powered by geothermal vents on the seafloor. Pattern interrupt. Notice what is missing. There is no obvious way for photosynthesis powered by a nearby star to dominate here. Life, if it exists, would likely feed on chemical gradients, heat from the interior, and maybe faint red glows from hydrothermal vents. Optimistically speaking, entire microbial oceans could thrive in this eternal twilight. This means we face a stark question. Are hydrogen-shrouded oases a common outcome of planet formation quietly hosting vast biospheres in the dark? Or are they rare, fin-attuned accidents that only occasionally arise when a forming planet keeps just the right amount of primordial gas? So, let's begin to weigh those possibilities and ask how we could ever detect such hidden worlds from light years away. Red dwarfs, dim suns, and the edge of the habitable zone so if starless, hydrogen-wrapped worlds might be possible. What happens when we turn the dimmer switch back up just a little? How faint can a star be before a planet effectively slips into the same twilight as a rogue world? To answer that, we have to talk about red dwarfs. Red dwarf stars are the most common type of star in the galaxy, small and cool compared to the sun, yet absolutely dominant in number. In the hunt for alien life, that matters, because if life can exist anywhere, odds are high that a huge fraction of it orbits these tiny embers rather than bright, sun-like stars. Their light is weaker and redder, and their Goldilocks zone sits incredibly close in. This means a potentially habitable planet has to hug the star so tightly that it becomes tidally locked. One side faces the star in perpetual day, the other side is trapped in endless night. Do we call that a sunlit world or a starless one? On the day side, the star can blaze like a permanent sunset. On the night side, the only illumination might be starlight reflected through the atmosphere, or faint auroras driven by the star's magnetic tantrums. It should be noted that for the faintest, ultra-cool dwarfs, even the day side is running on an energy budget far below Earth's. A planet in the habitable zone of such a star might receive only a fraction of the light we get, closer to a dim winter afternoon than a bright noon. The night side, shielded from direct starlight, begins to resemble the surface of a rogue planet, warmed mainly by internal heat and whatever energy the atmosphere can transport from the day. But while these systems are dim, they are not gentle. Red dwarfs can unleash powerful flares, bombarding planets with high-energy radiation that can strip atmospheres over time. Tidal locking can freeze air on the night side, or boil it on the day side, creating brutal temperature contrasts. At first glance, that sounds like the end of any realistic chance for an Earth-like biosphere. Optimistically speaking, though, the story is more nuanced. A thick, well-mixed atmosphere, perhaps with abundant greenhouse gases, can redistribute heat and smooth out extremes. Ocean circulation could carry warmth into the dark hemisphere, keeping water liquid under a permanent starless sky. In that case, the most stable, habitable regions might actually be the twilight ring or the deep night, not the blazing substellar point. So it's time to find out the truth about what these dim systems really mean for our spectrum of habitability. If life can adapt to the feeble, sometimes violent light of a flare-prone red dwarf, then we have a conceptual bridge from fully sunlit Earths down to almost starless worlds. Habitability stops looking like an on-off switch tied to a star's brightness and becomes a negotiation between internal heat, atmosphere, orbit, and whatever scraps of starlight the universe provides. In the next step, we will push that negotiation all the way toward true darkness. Can we ever detect life on a world we can't see? But if these worlds slide toward true darkness, how would we ever even know they are there, let alone alive? We are used to planets announcing themselves through their stars, a tiny dip in brightness, a slight wobble in the spectrum, a neat, repeating orbit in the data. Rogue planets and deeply star-starved worlds rip that playbook apart. They do not transit a parent star. They do not backlight their own atmospheres. Instead, they drift through the galaxy almost invisible, lit only by the faint infrared glow of their residual heat. Most of the time, that glow is far below what our telescopes can see. Occasionally, one passes in front of a distant background star, and its gravity briefly magnifies the starlight. That flash, called microlensing, might last days or even hours, then it is gone. No second chance, no long-term monitoring, just a single cosmic blink. This means that finding these planets is already at the edge of what we can do. Characterizing them is even harder. Yet, in the hunt for alien life, they might represent an entire hidden category of habitable real estate in the universe. So, let's begin with what we can actually detect. Right now, our best bet is heat. Large rogue planets, especially young ones, still leak internal warmth. A thick hydrogen-rich atmosphere could trap that heat and make the planet shine a little brighter in the infrared than bare rock. Current sky surveys barely skim this regime. But upcoming wide-field infrared observatories are designed to sweep huge areas of sky over and over, looking for exactly these faint, slowly moving points of light. If we can catch one nearby, we might even separate its light from the background and measure a crude spectrum. It should be noted that this spectrum would not be the clean, backlit transmission we enjoy when a planet crosses a bright star. Instead, we would be reading the planet's own thermal glow, trying to decode temperature, cloud layers, and maybe the broad fingerprints of molecules in the atmosphere. Could that glow reveal life? Indirectly, perhaps, an atmosphere in perfect chemical balance is usually boring. A habitable, Earth-like world is messy. Oxygen and methane together, or other out-of-equilibrium combinations, constantly replenished, would hint at active chemistry that is hard to sustain without some ongoing energy source, possibly biology. Optimistically speaking, if a hydrogen-shrouded rogue happened to drift in front of a background star, we might briefly see its atmosphere in silhouette and test exactly this idea. Future missions push this further. More sensitive microlensing campaigns could map the population of dark planets. Next-generation space telescopes could chase suspicious infrared sources, and in the very far future, fast interstellar probes might fly through the black, guided only by a whisper of heat, to sample a starless atmosphere directly. But while this all sounds ambitious, there is a sobering flip side. Even if starless biospheres are common, they may be almost invisible to us. Our estimates of cosmic life could be missing an entire class of worlds we barely know how to see. So it's time to find out the truth. If we cannot easily detect them from afar, what would it actually take to go to one of these dark planets ourselves? How much can we really claim right now? Before we launch our imaginary mission into interstellar darkness, we need to hit pause. How much of what we have said about life on a starless planet is nailed down by data, and how much is us carefully stretching what we know? In the hunt for alien life, it should be noted that we are still working from a sample size of exactly 1. We have 0 confirmed detections of life beyond Earth. We have not seen life on a rogue planet, on an icy moon, or even on a confirmed Earth-like exoplanet in a comfortable Goldilocks zone. This means everything in this episode rests on physics, chemistry, and analogies to the strangest corners of Earth's own biosphere. Some parts are on very solid ground. Chemosynthetic ecosystems at hydrothermal vents and cold seeps are real, measured, and thriving, powered by chemical gradients rather than starlight. Earth's deep biosphere, kilometers below the surface, really does seem to host vast amounts of microbial life. The physics of geothermal heating, tidal flexing, and radiogenic decay is well tested, and subsurface oceans on moons like Europa and Enceladus are supported by multiple independent lines of data. When we say a sealed ocean under ice can stay liquid for billions of years without much help from a star, that is not wishful thinking. But when we extend those ideas to a planet drifting between the stars, we move into more speculative territory. Do thick hydrogen atmospheres really survive ejection often enough to keep many rogue worlds warm? How many of them keep subsurface oceans rather than freezing solid? We do not know. Current microlensing surveys hint that free-floating planets may be as common as stars, or even more common, yet the error bars are huge. A modest change in those statistics could mean a galaxy rich in dark, potentially habitable worlds, or a much emptier cosmic ocean. There is another crucial uncertainty. A planet can be physically habitable and still completely lifeless. Liquid water, stable temperatures, and energy sources only create the stage. Life still has to appear, adapt, and survive early catastrophes. A rogue world might be sterilized by a giant impact before chemistry gets going, or lose key ingredients during ejection. Optimistically speaking, there could be countless hidden biospheres, but we must admit that many of these planets might be eternally sterile. So, let's begin treating these ideas as testable hypotheses, not fantasies. As telescopes improve, we will better constrain how many rogue planets exist, how massive they are, and whether they carry thick atmospheres or icy shells. So it's time to find out the truth. What concrete observations could actually reveal a warm, starless planet and maybe even hints of life across the deep interstellar night? A universe of hidden oceans. What we've learned tonight, if the sun really did fade to black, would Earth's story be over or just retreat underground? What we have seen tonight suggests that the answer is far stranger than a simple yes or no. So, let's begin by returning to that nightmare scenario. The star vanishes, the sky freezes, and within weeks the oceans start sealing over with ice. Photosynthesis collapses, the climate system unravels, and almost everything we normally picture when we say life on Earth disappears. But while the surface becomes an airless, frozen desert, the planet itself does not die. Deep below, geothermal heat and radioactive decay keep rock soft, water liquid, and chemistry moving. Around hydrothermal vents, chemosynthetic ecosystems could continue almost unchanged, powered not by sunlight, but by chemical energy welling up from the interior. In the deep crust, slow microbial communities might barely notice the loss of the star at all. This means that, even here, starlight is only one chapter in life's energy story. It should be noted that Earth already hosts thriving ecosystems that never see the sun. Hydrothermal vents, cold seeps, deep caves, and the deep biosphere kilometers down are all run on non-stellar energy sources: geothermal heat, tidal flexing from the moon, the steady drip of radiogenic decay, and sharp chemical gradients between hot, reduced fluids and cold, oxidized water. In the hunt for alien life, those gradients may matter more than the color of the sky. Once we accept that, the rest of the universe starts to look different. We talked about Steppenwolf rogue planets, Earth-mass worlds ejected from their original system, drifting between stars stars with thick ice shells hiding buried oceans. We explored the possibility of dark oases wrapped in dense hydrogen atmospheres, where internal heat alone could keep surface seas liquid despite the cosmic night. And we looked at icy moons and planets around dim red dwarf stars, where tidal heating and interior chemistry already prove that liquid water does not always need to sit in a textbook Goldilocks zone. These worlds show us that sunlight is helpful, but optional. So it's time to find out the truth about our central question. Does life need a star? The nuanced answer is no, not strictly. A planet can host a biosphere powered by interior heat and chemistry alone. But while that is possible, stars make rich, fast, complex ecosystems far more likely. Under a warm sun, energy flows are huge, evolution can run quickly, and surface biospheres can transform a whole atmosphere. In the dark, life may be slower, sparser, and deeply buried, yet also remarkably stable and long-lived. Optimistically speaking, that leads to a profound philosophical shift. Instead of a universe where life flickers only in thin shells around stars, we may live in a cosmos filled with vast, unseen biospheres, rogue planets, buried oceans, and dim red dwarf systems, all quietly alive. The galaxy could be less like a cold, empty void and more like a hidden, living ocean, with most of its creatures drifting where no sunlight ever falls. And if that is true, how would we ever know they are there? Your move, humanity, rethinking the habitable zone if the galaxy is really more like a hidden ocean than an empty void. Then, our old picture of habitability is suddenly far too small. In school, we usually see a neat diagram, a star in the middle, a thin green ring around it labeled the habitable or Goldilocks zone, and maybe an Earth-like planet drawn right in the middle. Warm, bright, simple, but while that picture is easy to remember, it quietly ignores almost everything we have talked about in this video. This means we now have to think in layers, not rings. A planet's star and orbit still matter, but so do its internal engines, radioactive elements, tidal heating, trapped primordial heat. An icy moon with a buried ocean, or a rogue world lost between the stars, might be just as habitable below the surface as TRAPPIST-1 is at the top of its atmosphere. It should be noted that on Earth, deep biospheres and hydrothermal vents already prove that rock, water, and chemistry are enough to keep life going without sunlight. So, let's begin to treat the habitable zone as a three-dimensional volume that stretches into the dark, around red dwarf stars, in the frozen outskirts of planetary systems, and out among the free-floating planets. There could be thousands of hidden shells where liquid water and energy quietly coexist. In the hunt for alien life, the next few decades are our first real chance to test this. Microlensing campaigns will scan the galaxy for the tiny brightening events that reveal rogue planets drifting with no star at all. New infrared observatories will search for the faint heat of thick atmospheres and warm surfaces even when there is no visible sun. And icy moon explorers at Europa and Enceladus will dive into jets and oceans that may be the closest analogs we have to starless seas. As this new data arrives, there is a more personal question. How does your sense of loneliness or connection change if life can thrive in places with no sky, no day or night, just endless rock overhead and a black ocean below? Does a universe full of dark sealed habitats feel more comforting because life is hard to extinguish, or more unsettling because we might never meet any of it? So it's time to find out the truth about our own expectations. In the comments, tell us, if you had to place a bet, where will we first find non-solar life? An icy moon in our own system, a world around a quiet red dwarf, or a rogue Steppenwolf planet we have not even seen yet? Optimistically speaking, even if every visible star went out, life might not. And as long as the universe keeps hiding possibilities in the dark, we have reasons to keep looking, to keep listening, and to keep asking better questions. Because what if the strangest discovery is not that we are alone or crowded, but that we have been searching under the wrong light all along?